You're driving along this function from left to right. Along your drive, there are several points of interest between A and L. All of them except for the start and the finish points relate to the steepness of the road. In other words, its slope or derivative. Very good. Now prepare yourself. I'm going to throw a lot of new terms and definitions at you all at once here. You shouldn't, however, have much trouble with these ideas because they mostly involve common sense notations like driving up or down an incline or going over the crest of a hill. First, notice that as you begin your trip at A, you're climbing up. So look at A, you're climbing up. Thus the function is increasing. And its slope and derivative are therefore positive. You climb the hill till you reach the top at B, where the road levels out. The road is level, so the slope and the derivative is 0. Because the derivative is 0 at B, point B is called a stationary point of the function. Point B is also called the local max or relative max because it's the top of the hill. To be a local max, B just has to be the highest point in its immediate neighborhood. It doesn't matter that the nearby hill at G is even greater. After reaching the crest of the hill at B, you start going downhill. So, after B, the slope and the derivative are negative, and the function is decreasing. To the left of every local max, the slope is positive. To the right of a max, the slope is negative. The next point of interest is C. Can you see as you go down from B to C, the road gets steeper and steeper? But then after C, you are still going down, but the road is actually gradually starting to curve back up again and get less steep. The little down arrow between B and C indicates that the section of the curve is curving down. The function is said to be concave down. So do you see between A and B, it's concave down, and B and C is concave down. A portion of the function that's concave down looks like a frown. So that's how you remember what concave down means. Looks like a frown. A sad face. Where it's concave up, between C and E, do you see it's concave up? It looks like a cup. You could fill it, right? Where a function is concave down, the derivative is decreasing. Where the function is concave up, the derivative is increasing. So the road is concave down until C, where then it switches to concave up. That's called the point of inflection. The point C is also the steepest point on the stretch of the road, the steepest points on the function, as well as the least steep points also occur at these points of inflection. Be careful, with function sections that have negative slope, point C is the steepest point in the neighborhood because it's the bigger negative slope than any other point nearby. But remember, a big negative number is actually a small number. So the slope and the derivative at C are actually the smallest of all the points in the neighborhood. From B to C, the derivative of the function is decreasing because it's becoming a bigger negative. From C to D, the derivative is increasing because it's becoming a smaller negative. Let's get back to the drive. After point C, you keep going down until you reach D, the bottom of the valley. Point D is another stationary point because the road is level there, and the derivative is therefore 0. Point D is also a local min, or relative min, because it's the lowest point in the immediate neighborhood. After D, you travel up passing E, which is another inflection point. It's the steepest point between D and G and the point where the derivative is the greatest. You stop at the scenic overlook at G, the point where the derivative is the greatest. You stop at the scenic overlook at G, another stationary point, another local max. Point G is also an absolute maximum on the interval from A to L because it's the highest point on the entire road from A to L. Going down from G, you pass another inflection point H, another local min I, then you go back up to J, where you foolishly try to drive over the peak. Your front wheels make it over, but your car's chassis gets stuck on the precipice, leaving you teetering up and down with your wheels spinning. Your car teeters at J because you can't draw a tangent line there. No tangent line means no slope. And no slope means no derivative. Or you can say the derivative at J is undefined. A sharp turning point like J is called a cusp. After dislodging your car, you head down the road, getting less and less steep until it flattens out for an instant at K. Again, note that because the slope and the derivative are becoming smaller and smaller negative numbers, on the way to K they're actually increasing. Point K is another stationary point because its derivative is 0. It is also another inflection point because the concavity switches from up to down at K. After passing K, you go down to L, your final destination. Because L is the endpoint of an interval, it's not a local min. Endpoints never qualify as local mins or maxes, but it is the absolute minimum on the interval because it is the lowest point from A to L. What'd you think about that? Yeah, so we're going to put all the words together in actual pictures here now. Okay, so absolute extreme values here. Absolute extreme values are either maximum or minimum points on the curve. They are also sometimes called global extremes or absolute extrema. Extreme values can be in the inside or the endpoints of a function. Okay, so in example 1, state whether there's an absolute minimum or maximum or none. So for number 1, absolute minimum at x equals 0 and no max. How about this one? Yes, so an absolute minimum at x equals 0 and an absolute maximum at x equals 2. What about this one? This is a circle not filled in. Yeah, so that means there's no absolute min, but there's an absolute max at x equals 2. Everybody good with that? Okay, so the next one, how about this one? Absolute min at x equals 0, no max. How about this one? Nothing. No max or min. Okay, so we're going to get into one of the many theorems coming up here. So the extreme value theorem. So you need to memorize this and put it on your those little cards I'm saying that you need to start. There's going to be lots coming up here. So if a function is continuous on a closed interval a, b, then f of x has an absolute minimum and an absolute maximum. Basically what it's saying here, that if you have a continuous function, they will always have a highest point and a lowest point as long as the endpoints are actually included. Okay, so this extreme value theorem, which we would abbreviate as EVT, guarantees both a max and a min. So if you ever have to justify why something's a max or a min, you would be quoting which theorem? Yes. So find how many extreme values the following three graphs have on D. So I'll give you a second to figure that out. Okay, how many did we get here? I hear extreme values. These are absolute maxes and absolute mins. So there's two. There's an absolute max right there. And yeah.
Probably the depth.
Huh? Okay, what about here? There's only one. This would be an absolute min. How about this one? None. Okay, everybody good? Okay. Local extreme values. So you need to know these terms here. So below shows a graph with 5 points where a function has extreme values on its domain. So there's local maxes and mins, and there's absolute maxes and mins, right? So an absolute minimum can also be a local minimum.
Oh yeah, and absolute maximum.
Can also be a local maximum as well. Yeah.
Not unless.
So the absolute max is the one in the entire graph, and the absolute min would be the lowest in the entire graph. Yeah, like in the neighborhood or whatever. Okay, so note local extrema will automatically include absolute if there are any. Okay, so here's our first famous mathematician, Fermat, Pierre de Fermat. My good French there. It's, yeah, Waterloo names their contests after a whole bunch of famous mathematicians. So in this course, we'll come up with a few. So he's best known for Fermat's last theorem, which states that there's no three positive integers, a, b, and c, that can satisfy a to the power n plus b to the power n equals c to the power n. So if you ever have a trivia, you'll know this is Fermat's last theorem. I know. This is his last theorem. So, well, that's why it's called his last one, so I would assume so. I don't know. But the theorem we need to know about is if a function f of x has a local max or min at c, and if f prime of c exists, meaning the derivative at c exists, then f prime of c equals 0. So think about that for a second. Why would this actually be true? What happens at a local max or min? The slope is 0. So basically, this theorem is basically, telling you that if it has a local max and min, then the slope has to be 0. So it gives you a starting for extreme values, which is also called the critical values. So critical points are points on the graph where the derivative is 0 or the derivative is undefined. Points on the graph where the derivative is 0 or the derivative...
What? Does not exist.
Oh yeah, I want does not exist. It's a... Sorry. Does not exist, because otherwise my English won't work. Does not exist are important to consider in many application problems of the derivative. That's the name of the unit we're on. The critical point f of x comma f of x is called a critical point of f of x in the domain of the function, and if f prime equals 0 or f prime does not exist. So the geometric interpretation of what is taking place at the critical points is that the tangent line is either horizontal, vertical. What would be the third one?
Doesn't exist.
Yeah, does not exist. And what would that be the case of? A cusp, a corner,
Vertical asymptote.
yeah, vertical asymptote. Okay,
Goes into this concept.
you guys got that right. Okay. Okay, critical points are not always extreme values. So do you see, this is not an extreme value, but the slope is 0. This is not extreme value, but the slope is undefined. Okay, stationary points. This is a point in the interior of the domain of a function such that f prime of x equals 0. A stationary point can be a max, min, or a inflection point. Steps for finding the max and mins analytically. Okay, so steps for finding a max and min analytically. You need to find the derivative of the function, determine where the derivative is 0 or undefined, which are the critical points. Find the value of the function at each critical point. If the domain is given in a closed interval, you also need to find the value at the endpoints, because the endpoints could be maxes or mins. And that's what a lot of people actually forget to do. They always find where the slope is 0, but they forget about the endpoints. Compare the y values, the largest function. Now, when I was stating before the max value was at x equals 0, the value of the maximum is the actual y value, right? So we're supposed to be comparing the y values. And the smallest is the min. So let's do this. So here's a graph of y equals x squared plus 1 with the domain from -1 to +2. You're supposed to find the absolute minimum and maximum. So again, the steps are find the derivative. So we won't have this graph necessarily in front of you, right? I just put this there so you can see visually what we're actually finding. So what is my derivative? Y prime equals 2x. So now the next step is to find where the derivative is either undefined, which there's no way that 2x could ever be undefined, right? The only reason I do get something undefined, it would be if it's in a denominator position, right? Okay, we could find where it's 0. So 2x equals 0, so that means it is... there's a critical point at x equals 0, but I won't know what the value is until I actually calculate it. I just know something's going on at 0, okay? Which I can see right there. There's a local min, right? So in order to know what that is, I need to plug it into y equals 0 squared plus 1. So that means at 0, there's a y value of 1 right now. I don't know if it's the max. I don't know if it's the min yet. I just know it's 1. So the only other thing, because there's no other, like sometimes you'll get a quadratic, so you might get 2 values where something's going on, or cubic. The only other thing I can do is check the endpoint. So I'm going to check when x is -1. So now I'm going to do the endpoints. X equals -1, y would be -1 squared plus 1, which is 2. So that's higher than that, so that can't be a max. This could potentially be a max because it's the highest one so far, but I know visually it's not the highest on the whole thing, right? Okay, the other one is x equals 2, so y equals 2 squared plus 1, which gives me 5. So bingo, that is the highest. So that means that is the absolute max at 2, 5, and the absolute min is at 0, 1. All right.
Is there a local max?
So this technique is only finding absolutes. Okay? So you could say, yeah, at the endpoints. Okay. So find the critical points of this mess. Now I don't have a graph, so you can't actually cheat and see where they are. But you do know from grade 12 what some kind of graph that's a power 4 kind of looks like, a picture in your head. First thing is to find the derivative. So we get 12x cubed plus 60x squared minus 72x.
She's been teaching math.
Well, no, it's just a quick multiply. Okay, so the next step is what? Setting it equal to 0. Does everybody understand there's no way I would get an undefined slope here? So the only thing I can do is 0. Now there is no set domain, so what does that mean?
You don't have to check any endpoints.
You don't have to check any endpoints because there is no endpoints, right?
Yeah.
Yeah, the domain is all real numbers, right? So 0 equals 12x cubed plus 60x squared minus 72x. So what did we learn in grade 12 pre-cal? You can take out a 12x. Very good. So we get 0 equals 12x, and we're left with x squared plus 5x minus 6, and that factors to be not negative 6 and 1. It would be plus 6 and x minus 1. I don't know if that's what you meant, which means I need to check what? X equals? Yes, don't forget you're getting a value right here of 0. So we're going to check 0, negative 6, and positive 1. Okay? So just for simplicity, I'm going to give you the values here. So f of 0 is 7. F of 1 is negative 6. And f of negative 6 is negative 1721.
I think that's the...
So, well, yeah. So, what do you think out of all this?
Well, we got the max and the min.
7 is
negative
min.
1721.
Negative 1721.
So, is this an absolute max or min?
Well, how do you know?
Well, how do you know? You can. Let's go back to the theorem here. This shows you only that there's local maxes or mins, right? And the other theorem said, in the extreme value, it said that in a closed interval. Was this a closed interval? No, so we are not finding absolute value. I said the absolute. When they give you a domain restriction, yes. But what in this question here, essentially what it's showing you is we have at negative 6, we have some really low point here. And at 1, we have another low point, right? And at 0, I have this. So do you remember what a polynomial that has a positive leading coefficient looks like? Right? So it looks like this. So what do you think these are? This would be local min, and this would be a local max. So don't say it's absolute, right?
But isn't plus negative 6 also local?
Oh yeah. Local min. Very good. So sorry, because we know what the graph looks like, we could conclude that this is an absolute min. But based on any of the theorems, we can't do that unless we know what the graph looks like. So this happens to be an absolute.
But we wouldn't be marked.
Yeah. I need to find out about that. Okay? Okay. You guys have just one more page left?
We have 5 minutes.
And we have 5 minutes, so let's go. Find all the points in the domain that it does not exist. So, What's the domain for this function? I'm sorry, it has to be greater than 0. So x has to be greater than or equal to 0. Okay? Shh. Okay, so f of x is 9x to the power a half plus x to the power 3 over 2. So what's my f prime going to be? 9 over 2 x to the power negative a half. Okay. So I'm going to rewrite this so you can see the restrictions here. So does everybody see this would be 9 over 2 square root x. And then this would be 3 over 2, and this would be square root x on top. So where would you actually have an undefined region? Right there. So it's undefined at x equals 0. It's just saying find all the points in the domain that it doesn't exist. So I should say it doesn't exist at x. So does not exist at x equals 0. Okay, next one. What is this domain restriction?
X equals 4.
X has to be less than or equal to 4, right? Inside the radical has to be greater than or equal to 0. If you solve, it has to be less than or equal to 4. Okay, so this would be a chain rule. So f of x equals 4 minus x to the power a half. So f prime of x would be, how about 1/2, 4 minus x to the power negative a half times negative 1. Yes. Okay, so let's simplify this. So this is going to be the square root of 4 minus x on the bottom with a 2 on the bottom and a negative 1, say, on top. Okay, so does not exist at x equals 4. So you got to watch just because your domain is. Okay, so it says find the max and min of this. So how do we do that? Derivative? What's the derivative of sine x? So cos x minus sine x. So we're going to set it equal to 0 and solve. 0 equals cos x minus sine x. So that means wherever sine x equals cos x in the domain 0 to 2 pi, that will be some critical points there. So that means x equals pi over 4 and 5 pi over 4, yeah. But we also have to test critical points because now we have a closed interval. Does everybody see we have a closed interval? Okay, so that means we need to find f of pi over 4, which for time's sake I'm going to give you the value is root 2. F of 5 pi over 4, which for time's sake I'll give you as negative root 2. F of 0 is 1, and f of 2 pi is 1 as well. So what does that mean?
Well, we got minimum and
Now this is a closed interval, so we can actually say it's absolute, right? So absolute min is here. And what's bigger, root 2 or 1? Root 2. So this would be an absolute max. All right. Okay, let's see if we can do this in the little amount of time we have. Okay, f prime of x. Find the derivative. What's the derivative? 4x cubed minus 16x. Set it equal to 0 and factor. I can pull out a 4x, and I'm left with x squared minus 4, which also factors is 4x times x minus 2, x plus 2. So that means this is an open interval, right? It's all reals. So the critical points will be at 0, 2, and negative 2. Again, for time's sake, f of 0 is 0, f of negative 2 is negative 16, and f of positive 2 is negative 16.
Wow.
So what does that mean?
You just got classic.
Know where the
Local minimums.
and local max.
Yeah, we only know local. So these would both be local min, and this would be a local max. And then once we show it graphically, we could conclude that, what else is going on there. For anybody that has textbook, the pages are different for the answer key, right?